So we'll start with some like metallurgy of some important metals. First, I'll be starting with extraction of iron. So the important or the principal ore of iron would be hematite. So what will happen here? You first have the iron ore, which is hematite, whose formula is Fe2O3. We do roasting or calcination. So after performing roasting or calcination, you have a blast furnace in which you are going to send hot air plus oxygen. You will also add calcium carbonate and coke, where reduction of iron by carbon and carbon monoxide will happen. As a result, you have pig iron and slag, which is the impurity. So this is the flow chart we'll see in detail. So once you have the ore of oxide, as the like hematite is oxide ore, no? So once you have the oxide ore of iron, after concentrating it through calcination or roasting, okay, that is we are trying to remove the water. To decompose it, to decompose these carbonates and sulfides. So we are first, after calcination, you are going to mix it with limestone and coke and send this to a blast furnace from its top with the help of an arrangement. So oxide here, what happens, because you are adding the coke or anything, it is going to reduce the particular compound into the metal, the respective metal. So thermodynamics will help you to understand how the coke reduce the oxide and why is the furnace chosen. So what is the reaction that's happening is you have iron oxide reacting with carbon, where you have iron and carbon monoxide. Okay, so you can see after this the iron, which is in solid, can give rise to iron plus oxygen. Carbon plus oxygen is giving rise to carbon dioxide. The reaction that have taken place. How this is the one which helps you to understand how coke reduces the oxide or oxide. So this is the reduction step. What happens here? You have simpler reactions which happen. First of all, this is reduction of iron oxide which happens here. Here the carbon is oxidized. Different reactions that are involved in this. So what happens? When both the reactions takes place to yield a reaction, so coke is trying to reduce the iron oxide and it itself will be oxidized to CO. In the similar way, reduction of Fe2O3 and Fe3O4 are also going to be discussed here. Can I clear the screen? I'll draw the whole diagram, you'll understand. As I said, we are using a blast furnace for this reaction. So in blast furnace, what happens? In blast furnace, reduction of iron oxides take place. In different temperature ranges. In different temperature ranges. So what happens here, As I said, hot air or oxygen is sent, no? This is blown from the bottom of the furnace. I'll draw the diagram. And coke is burnt to give the temperature up to 2200 Kelvin in the lower portion itself. So burning of coke only gives most of the heat required. Burning of coke supplies most of the heat required in the process. So what happens here? Carbon monoxide and heat, they move to the upper part of the sun. I'll show you the diagram also. It moves to upper part of the furnace. So what happens there is, in the upper part, temperature is lower and the iron oxides coming from the top are reduced in these depths to iron oxide. So I'm just clearing it. I'll draw the diagram. Oxygen and air are sent. Coke. Here we are sending over limestone, everything through this. You have something where exhaust gases come out. CO and CO2. So at this place, what happens? 3Fe2O3 with CO gives rise to Fe3O4 plus CO. Next, Fe3O4 with the CO when it reacts gives rise to FeO plus CO2. So CaCO3 is giving rise to CaO and CO2. The CaO and SiO2 are giving rise to CaSiO2, which is called slag. And the FeO is reduced with CO, where you get Fe plus CO2. Coke reacting with carbon dioxide, we have carbon dioxide gas. C plus O2 is giving rise to CO2. FeO plus carbon gives rise to Fe plus CO. All these are the reactions that occur. So the reactions, whatever occurred, they all have proceeded in different temperatures at different temperatures and different stages. What happens when the air is passing? No, it doesn't reach to higher place. So what happens at 500 to 800 Kelvin? As Fe2O3 plus CO giving rise to 2 Fe3O4 plus CO2 takes place. So Fe3O4 plus CO giving rise to 3 Fe plus 4 CO2 also takes place. Similarly, Fe2O3 plus CO gives rise to FeO plus CO2. What happens from 900 to 1500 Kelvin? Carbon reacts with carbon dioxide. FeO plus CO gives rise to Fe plus CO. Limestone also is decomposed. Also, I already wrote the reactions. I'm just telling you the temperatures. So whatever pig iron, I have a very small part to write, and that will be the end of iron extraction. Small part only to write with 4-5 statements. So I'm clearing it. Next we have, what am I saying? So whatever iron is obtained, the iron obtained from the blast furnace, from blast furnace, it contains 4% of carbon and many impurities, which are sulfur, phosphorus, silicon, manganese, and all. And this is pig iron. And cast into variety of shape. But that is different. Cast iron is different. Is made by melting this pig iron with scrap iron and coke using hot air blast. Also about cast iron, it is hard and brittle. So after this, very important, wrought iron or malleable iron is purest form of commercial iron. How is it made? It is made from the cast iron when the impurity oxidizing the impurities in a reverberatory furnace lined with hematite. So why? Hematite is going to oxidize the carbon to carbon monoxide. That's why. So continuation here is Fe2O3 is going to react with that carbon and convert it into Fe plus CO. That is why we use it. And CaCO3 is added in this as flux. And sulfur, silicon, phosphorus are oxidized and passed as slag. That's all about the iron. All of you, if you let me know that you're done copying this iron completely, we'll go to copper. I'm clearing it. Next, we have extraction of copper. So extraction of copper, how do we extract it? We extract it first from cuprous oxide. Obviously, copper 1 oxide. It is easy to reduce oxide ores of copper directly to the metal by heating with coke. So sulfide ores are roasted or smelted to give oxides. So copper sulfide reacts with oxygen to give copper oxide plus acid. So the oxide can be reduced to copper using coke. Cu2 plus C gives rise to Cu plus Co. This is from the simple cuprous oxide. Next, we have the actual method, that is from copper glans or copper pyrites. So I'm clearing it. Let's look at from copper glans or copper pyrite by self reduction. So what happens? First, ore is heated in reverberatory furnace after mixing it with silica. So what happens in the furnace? In the furnace, iron oxide slags off, means convert into slag as iron silicate and copper is produced in the form of in the form of copper matte. Copper matte means it contains CO2s plus FeS. So what is this copper glance? You know, it is CuFeS2. It's reacting with oxygen. We have Cu2s plus FeO plus SO2. Cu2s plus FeO plus SiO2 gives rise to FeSiO3 plus Cu2s. This is only the matte. This is the fusible slag. So copper matte is then changed into silica lined converter, which is called Bessemer converter. Remember, Bessemer converter is used in preparation of what? Extraction of what, like that. Some silica is added. Some silica is also added. And hot air blast is blown to convert the remaining FeS2, FeO, and Cu2s and Cu2O to copper. I'll write the reactions. But what happens in the reverberatory furnace? So when you have like this, there's an outlet where waste gases pass through. This is the furnace. So whatever is there, it's put on this. Furnace. This is a fire brick. You might have seen in olden days. So that's how a furnace looks like. Like you have a space to heat it. Let me know if you're done, we'll go forward. I'm clearing. So what happens? As this is copper, like iron sulfide, it reacts with oxygen, forms iron oxide and sulfur dioxide. Copper S reacts with oxygen. FeO plus SiO2 gives rise to FeSiO3. With all the reactions involved, gives rise to copper and sulfur dioxide. Self-reduction. Self-reduction. So what happens here? In the Bessemer converter, you have stand like this. So hot air plus sand. This is molten matte plus sand. This is Bessemer converter. The lining of it. Lining is acidic lining. Acidic lining is SiO2 lining. All the waste gases come out like this. So whatever you can see all this present. So you get actually solidified copper. So it's solidified copper, and there is evolution of SO2. So this looks like blisters. That's why it's called blister copper. From Bessemer converter, you get blister copper. So this is the second type of extraction from copper pyrites or glass. Third, we have low grade ores and scraps from which you can extract copper. Third method. Okay. Next we have from low grade ores and scrap. So leaching, it is a chemical method of the Cu2O, which is cuprite, or copper glance, which is Cu2S, with the dilute SO4, with dilute H2SO4 in presence of air. It gives you of copper sulfate, and impurities present in the ores remain undissolved in the acid. So example, leaching of malachite, which is CuOH twice and CuCO3 plus dilute H2SO4. gives rise to a solution of CuSO4. So 2Cu2O plus 4H2SO4 plus oxygen gives rise to 4CuSO4 plus 4H2O. Same Cu2S plus 4H2SO4 gives rise to 4O2, sorry, plus O2 gives rise to 4CuSO4 plus 4H2O plus SO2. Same with malachite green also. But how do you get the copper out of the CuSO4? So copper can be recovered from CuSO4 either by electrolyzing it where copper is collected at cathode, or second, by treating with scrap iron as being more reactive than copper displaces. That's all. Is the third method. Complete. I'll wait for 1 minute. We'll go to extraction of lead. I'll clear it. I'm clearing it. We have extraction of lead. First, from PBS, which is lead sulfide, which is an ore. There are two methods. Of extracting the element. Roast in the air. With coke or CO in blast furnace. Next is PBS. You know all heterogeneous. What is roasting and all? Blowing air through it. Self-reduction. O2 is air. These are the two methods of extracting the metal. I'm clearing it. So chart will be like, you have galena. Because it's a sulfide ore, you have froth flotation. Roasting, partial roasting. Smelting plus carbon reduction. In this case, self-reduction. In both ways, I'm getting impure lead first. This has to be refined. Liquation. Desilverization. Electrolytic refining. That's it with lead. Zinc. From ZNS. Zinc blend. A. Ore is roasted at temperature 1200. Excess air. The reduction of ZNO is done with coke. So ZNO plus C gives rise to Zn plus C. So metal is distilled and collected by rapid chilling. That's all. We have one small chart about zinc. I'll clear this one right there. Electrolytic refining and zinc. That's all. Let me know once you're done. We have extraction of iron for tin. Next one. Extraction of tin. Does it right? SnO2. So first, we have purification. A is crushing and concentration. B is electromagnetic separation. 3 is roasting. What is happening here in electromagnetic separation? So in roasting, what happens? Anyways, crushing and electromagnetic separation. So roasting means what happens? It is heated in the presence of air. And also sulfur is removed, impurities. Sulfur is removed as SO2, arsenic as As2O3, antimony as Sb2O3 are also removed. Other impurities of pyrites of copper and iron are converted to oxides. Like CuS plus O2 gives rise to CuSO4 and FeS plus O2 gives rise to FeSO4. That is the roasting. So 1, 2, 3. Fourth is leaching. Sulfates of copper and iron are dissolved in water. Fifth method. Fifth is washing. Ore is washed with water to remove finer iron oxide produced in roasting. So this ore contains 60 to 70% of SnO2. This is called black tin. After this, we just have another method called smelting. Because SnO2, oxide of tin we got, but we need tin, no? So this is the first. Under purification, we got this. Next, we have smelting. Next, we have smelting. Smelting. B part after purification. So SnO2 is reduced to the metal using carbon at 1200 to 1300 degrees Celsius in electrical furnace. So product contains traces of iron which are removed by blowing air through molten mixture to oxidize the FeO which floats on the surface. So SnO2 plus carbon gives rise to Sn plus CO. And iron plus oxygen becomes 2FeO. So when you have a Shaftin as the product. Please continue. So we'll continue with magnesium extraction in the coming class. I know there's a lot to write and remember. Metallurgy is actually a very dry topic where we have to keep writing. I know all of us are tired writing. I'll see you again in the next class. We'll see if we can complete the metallurgy chapter. Thank you.